And as I was explaining already before, the talk will deal with two different kinds of physics. One is flavor physics in the hadron sector. That was what I was telling you about. The other one will be Higgs physics. Okay, so what the latecomers missed was this first part of the introduction. Now I will run a second introduction which has more to do with electroweak symmetry breaking. That will be the motivation for Higgs studies. Then I will discuss some of the technical aspects. What happens when you try to deal with the renormalization of these four-fermion operators that appeared in flavor physics and will appear in electroweak symmetry breaking, and how you tackle renormalization from a non-perturbative point of view. And then I will show some results that have implications for these two different fields of standard model physics. One will be the appearance of a large enhancement due to renormalization group running, enhancement of or depression, depending on how you see it, of beyond the standard model corrections to neutral meson mixing. And the other one will be the role of anomalous dimensions of four-fermion operators in some specific strong electroweak symmetry breaking model, which is minimal multi-technique. So you missed the flavor physics part, but most people were here by the time I discussed this, so I can skip it. Let me now come to Higgs physics. So now we know that there is Higgs, and it's been with us for more than 2 years now, but of course, as it often happens, once you get something new and exciting, more trouble starts to arise, or if you prefer more interesting stuff. What we are after now is to try and understand what kind of beast this Higgs-like particle is. And this is a summary of the current status of the measurement of various Higgs couplings in Atlas, where the bottom line is things look pretty much standard model, but precision is still relatively poor. And the big question that I will be asking here is whether the standard model weak coupling elementary scalar field description of this kind of physics is really what we are seeing, or there is room for something different. Okay, so let me start with a few statements. I will keep in mind that there are two different kind of models for electroweak symmetry breaking, which I loosely dub weakly coupled and strongly coupled. Weakly coupled models basically means that you introduce elementary scalar fields as in the standard model, and you couple these fields to fermions via Yukawa couplings, and you introduce a potential so that you induce electroweak symmetry breaking and so on, and you can do that basically without supersymmetry, which tends to lead you to the hierarchy problem, or with supersymmetry, which may have looked natural at some point in spite of the huge amount of soft breaking parameters you have, but nowadays it starts to be questionable whether supersymmetric models are natural after all, because the soft breaking parameters are subject to quite some tension if you don't want to have fine-tuning in SUSY models. The other class of models would be ones where electroweak symmetry breaking is triggered by some strong coupling dynamics at high energies. The electroweak symmetry breaking degrees of freedom are actually Nambu-Goldstone bosons coming from that strong dynamics. And one crucial point I want to make here is that whatever you do along these lines will necessarily relate electroweak symmetry breaking and flavor. So two problems that look separate in these kind of models come together in this world. And the first one open question here is, where does the Higgs come from? Many of these models do not necessarily have a transparent manifest candidate for a Higgs boson, and you have to work that out a little bit. Let me discuss some jargon. Right? We were discussing this before lunch, actually. In strong electroweak symmetry breaking, I often find there is some terminological confusion, so I will attempt to clear that with a couple of slides. First term is technicolor. Okay, so technicolor basically means the following. Think of QCD. Okay, standard model, you have QCD. QCD alone breaks the SU2 left chiral symmetry spontaneously because a condensate is formed. Your weak bosons couple effectively to pions, which are the Goldstone bosons of the breaking, and that induces a mass for the W boson, which is proportional to the pion decay constant, which happens to be about 30 MeV, which is way too low to explain electroweak phenomenology. But tells you that the qualitative features of dynamical electroweak symmetry breaking are already there in the standard model. Technicolor is basically the idea that if you have some strongly coupled interaction at high energies, maybe QCD-like, then you can play the same game and have electroweak symmetry breaking. As far as if you have something similar to QCD, the corresponding pion decay constant, or the decay constant of the technopions that would form in this sector, is of this size. That would give you the correct W mass. So what you have introduced here is a coupling between weak bosons and these high energy quarks, okay, whatever they are, technicolors. So this is what is normally called technicolor. Now, then there is also extended technicolor. What is extended technicolor? That's easy. Once you have this coupling, you actually introduce masses and mixins for standard model fermions. Okay? Because you can start having this kind of diagrams. You can have that in a minimal model or not, but it is very natural to introduce that. So the moment you have this new high energy interaction, you will start forming condensates, you will start getting contributions, mass-like contributions to standard model fermion propagation, and that will induce masses and mixins, that will induce flavor. Now, the point, and I will discuss this more in detail, is that it is quite hard to reproduce the kind of hierarchies between masses and mixins that you observe in the standard model with just basic forms of couplings. This is very neat when it comes to electroweak symmetry breaking, but when you try to play the flavor game, you have to complicate the structure of this high energy sector considerably by introducing new kind of couplings, new interactions, and so on and so forth. But the essence is the same. Once you have strong coupling at high energies, you will have the flavor game incorporated. Finally, there is composite Higgs. Composite Higgs is usually spoken of as a way to concentrating on the physics of the Higgs boson. Okay, so one is not focusing on electroweak symmetry breaking, one is not focusing on flavor. What you're focusing on is the possibility that the Higgs boson is not an elementary object, but it is something that comes from some unknown high energy sector, and it is something similar to a Goldstone boson. Okay. Of course, my point here is that whereas in a phenomenological context, technicolor, extended technicolor, and composite Higgs are commonly thought of as different things, so one could listen to talks about composite Higgs models where they are saying simultaneously that technicolor and extended technicolor are completely out of the game. I just want to point out that these three jargon terms are all coming from the same basic stem. You have some strong interaction at high energies that will break electroweak symmetry, that will induce flavor, that will certainly generate composite scalar states that may or may not have the properties of the Higgs boson, and these are all aspects of the same game, which I will consider in full generality here. Okay. And this is just an illustration of what is the kind of room these models have available with current data. This comes from an analysis by Adam Falkowski and other people, where they were considering beyond the standard model scenarios in the Higgs sector using pretty generic effective Lagrangians and parameterizing beyond the standard model effects in terms of some modified couplings with respect to the standard model ones. So these C's here would be 1 in the standard model. Whenever you see deviations from 1, that means that you have some new physics that is changing the value of these effective couplings. And they run some analysis which show you in some particular slice of parameter space where for instance, you have the same fermion couplings and you leave their value and the value of this vector coupling here free. They see that around 1, which is the standard model value, different constraints coming together leave quite significant freedom so far. Okay, you can deviate by as much or as maybe 20 or 30% in some directions from the standard model. This is physics which is not very well measured yet. So this is basically telling you that there is quite some room for this kind of composite model, in spite of the fact that measurements so far go more along the lines of simple standard model physics. Good. So let me come back to some details of how Technicolor and extended Technicolor, the terminology we adopt from now on, work. This is a cartoon of the mechanism for electroweak symmetry breaking, which is postulated in the Technicolor paradigm, okay, where you have the standard model electroweak group that is broken via quantum effects, both by QCD, giving some small contribution to W and C masses via pions, and some high energy Technicolor sector where technipions provide the bulk of the mass. The reason this is good enough for generating vector boson masses is that asymptotic freedom in whatever Technicolor theory you have here would generate a gap between the ultraviolet and the infrared that generates the scale separation that you see in the standard model. This has a few problems, however. One classical problem is that this kind of dynamics tends to change the oblique parameters in electroweak corrections in a way that generates tension with electroweak precision measurements. I mean, this is something which is not very well known. This is non-perturbative physics, so whatever is known here typically comes from large N approximations and so on. These corrections to oblique parameters are not well computed, but still it is something people have in mind. I will skip this scale problem. It will not be very relevant for what follows. What is really bad about Technicolor is that there is a serious problem when it comes to flavor. Here you immediately generate effective flavor changing neutral currents which are not suppressed, and that induces a huge tension with standard model properties. The underlying problem actually is that it is very hard with this kind of Technicolor dynamics to generate the hierarchies you observe in the standard model fermion sector. As I was saying before, that's the reason to introduce extended Technicolor. This is again a cartoon, this time by Luigi Del Debbio, and extended Technicolor is alleviating, hopefully, the flavor problem posed by Technicolor by complicating the interactions in the strongly coupled sector. And my point here, my main point, is that no matter what you do in this extended sector, you are bound to run into trouble when you have theories that are QCD-like. This is already in this diagram here. Anything that is QCD-like has a well-defined scale. This is the lambda Technicolor here. Any quantity in this strongly coupled sector will be given by some power of this scale times order 1 numbers. Every physical quantity will be generated by this well-defined scale, and then you will have trouble generating hierarchies. It is hard to start with one number and generate widely different numbers. And thus, that manifests itself both in the case of masses, where you induce standard model masses via some extended technicolor condensate, or in the case of four-fermion couplings, where you collapse one of these high-energy interactions and get some effective vertices, which may in particular be non-suppressed flavor changing neutral couplings. And what this boils down to is the fact that in order to build a realistic extended technicolor sector, you end up introducing roughly as many interactions as standard model flavor parameters, which is not what you want it to do. You want something that is more fundamental than the standard model, so you don't want to replicate the large amount of degrees of freedom you have in the standard model. And the underlying reason for this is that QCD-like theories do not generate enough of a gap between the infrared and the ultraviolet. Now, how can you solve for that? You can solve that by changing the nature of the strong sector. This is a summary of what I was saying. This is a running coupling that works as in QCD. You have some logarithmic running that increases the coupling as you go to smaller scales, and there is some characteristic scale lambda. And you run into trouble in the flavor sector. You don't know very well what the Higgs is. And the way you can solve or alleviate flavor problems is to change your paradigm. Instead of dealing with a theory that is QCD-like, where you have this logarithmic running and one well-defined scale, you may consider a theory which has an infrared fixed point, a non-trivial infrared fixed point. That means that the coupling will run from the trivial ultraviolet fixed point to some fixed value in the infrared at very low energy scales. Physics around this point will be conformal, there will be scale invariance. This theory will still have a characteristic scale as seen from the ultraviolet, which is the asymptotic freedom scale. It is the scale at which the theory becomes weakly coupled. And in order to do proper model building, of course, you don't want to have this exactly conformal infrared physics. This has to be spoiled at some point by something that makes the coupling rise and binds this interaction. But one point I wanted to make is that you don't need to play fancy games in the high energy sector to do this. Standard model physics, for instance, will do that for you. Once you switch on standard model interactions, you will naturally have some infrared scale which spoils your conformality. And the gain here will be that if these scales are separated well enough, then you have some good potential to generate flavor hierarchies. Why? Because once you get this conformal sector, whenever you take some quantity, for instance, an extended technicolor condensate that generates masses, and you run it between the ultraviolet and the infrared scales, instead of this kind of logarithmic enhancement, you will get a power law behavior controlled by the anomalous dimension of the operator you're interested in this case, the anomalous dimension of the condensate. So since this is much larger than its log, it is much easier in this way to generate hierarchies. Of course, what you don't know is whether you generate the right hierarchies. For that, you need to compute anomalous dimensions in some specific model. Exactly the same happens in the case of four-fermion flavor couplings. Instead of logarithmic running, you get power running. You get a much wider separation of scales and a good potential to generate flavor. Now, to conclude this introduction, let me explain to you why I will focus on four-fermion operators living in some of these strongly coupled high-energy sectors. Here is the Higgs-Yukawa sector of the standard model. This is the kind of Lagrangian you would write in weak coupling models with up and down quarks coupled via the Higgs field and some Yukawa couplings here. In these models, the Higgs field is an elementary scalar. It has engineering dimension 1, so this has engineering dimension 2, and since you have weakly coupled physics, you expect anomalous dimensions to be small. So the actual dimension of this thing will be slightly different from here. Now, in strongly coupled electroweak symmetry breaking, this is the kind of terms you get in the Yukawa-Lagrangian. These are effective interactions between standard model fields and technicolor sector fields suppressed by the square of the UV scale, and these are your Yukawa couplings here. Now, the role of the Higgs field, so we change notation in the same line, will be played by this thing, which is called psi here and q here. This is a dimension 3 operator. And this thing, which before had dimension 2, now will have dimension 6. And the fields involved are strongly interacting, so there is no reason for you to believe that anomalous dimensions are generically small. When you compute the anomalous dimension contribution, this thing may deviate from 6 significantly. This is one example where this thing may come into play in using a very spectacular physics effect. Okay? So this is the top Higgs coupling as discussed in this work here. And what they are doing here is to work out explicitly, using some conformal field theory technology, what are the corrections to a standard model like Yukawa coupling coming from the conformal sector. Okay, so this would be the leading interaction at low energies. This is your standard top Yukawa coupling. And this is the leading correction in some expansion in terms of the properties of the high energy sector. Okay? And you get this composite operator here, which embodies the correction. You can work it out using bootstrap techniques, and this is the kind of correction to the Yukawa coupling you will get. And this is controlled by this power of the ultraviolet scale, where this is the scaling dimension of H, of the scalar composite fields that plays the role of your Higgs boson. So, for instance, if the scaling dimension gets into some window, which is far from the perturbative regime, but may be possible in a strongly coupled model, then this thing here becomes a relevant deformation of the conformal field theory, and you get a wildly different infrared physics. You get strongly coupled Higgs in the low energy regime, and you will get sizable deviations from what the weakly coupled standard model tells you. Okay? Something very similar, and this I think is the last slide of this first part, happens if you start considering flavour corrections. This, for instance, is a four-fermion correction to the fermion part of the Lagrangian. It is again controlled by some power of the new physics UV scale, where again the anomalous dimension of this scalar effective field appears, and whether or not you get the correct flavor changing neutral current suppression depends enormously on what is the value of the relevant scaling dimension. So the conclusion of all this is that in order to do proper model building for strong electroweak symmetry breaking, the anomalous dimensions of these four-fermion operators have an important role, and one has to determine them. Okay, that brings me to the second part, which will be shorter, hopefully, which is how you can determine anomalous dimensions of these four-fermion operators that will contribute either to flavor physics in the standard model or to physics of strongly coupled electroweak symmetry breaking tensors. So imagine you take a generic four-fermion operator. This four-fermion operator is in general a product of two quark bilinears, which are traced over spin, flavor, and color, that is indicated by these parentheses. And here there is an internal spin and flavor color structure. Okay? This comes from the fact that these effective operators will always come from an operator product expansion where you have collapsed two currents, and these matrices here tell you what kind of couplings you have here. Now, it is a general theorem of renormalisation that whenever you have a composite operator, it will mix with all other operators with the same transformation properties under all symmetries. So what happens in general is that given some operator you are interested in, you will have to find all the operators that have the same transformation properties under all symmetries. And renormalized operators will be linear combinations of their operators that can therefore mix, maybe in complicated ways, under renormalization. And I will always work in mass-independent schemes. This has the advantage that one does not have to bother about some technical complications involved when you have mixing with lower dimensional operators. Okay, I won't enter into that. What I will be dealing with is operators that are not affected by mixing with lower dimensional operators, and it was shown already several years ago that a completely general way to determine their anomalous dimensions is to consider operators that have formally 4 distinct flavors and live in the chiral limit. So this is the kind of operator where you have flavors 1, 2, 3, 4 here. These are spin color traces, and the only thing you have here is some specific spin structure for the operator. And you can work out all the details, and out of all the possible operators with spin and color structures here, you end up in QCD, and I will come back to this later because in models with adjoint fermions this is different. You end up with only 10 possible operators. These are these 5 operators here, each of which comes in plus and minus version. And plus and minus means that you take the same operator with the same spin structure, you exchange flavors 2 and 4, and you either subtract or add it to this operator here. So these 10 operators are all the possible dimension 6 operators which are Lorentz invariant and which are independent. You cannot transform them into each other by algebraic identities in QCD. And each of them can be split into a parity even part and a parity odd part. That is quite easy. Now,
sorry, can I ask something?
Yep.
Here you're not, I mean, have you, by after fielding, what about color structure here? Are you?
I will come back to that later because in the adjoint case it is different and I will discuss that in detail then. So let me postpone this. Okay.
But here you're not thinking about color yet at all.
Basically,
you
what happens is that if you introduce color here,
yeah.
you can use color identities.
Yes.
Okay, and then use fields identities between spin matrices to rewrite operators which have some non-trivial color structure in terms of operators that have trivial color structure.
Yes.
And that is what gives you these flavor exchanges here. I will discuss this anatomy in detail for adjoint fermions because then that is something new. In all cases, you can get rid of color structure. The point is what kind of spin structure that generates. Now, how do these guys renormalize? Okay, these operators here, in principle, can mix among them. And one has to identify what are their transformation properties under all relevant symmetries, chiral symmetry, discrete symmetries, and so on and so forth, and find the mixing structure. Okay, so the result that was found 15 years ago is that the renormalization pattern has this form. Okay? First of all, plus and minus operators don't mix. They don't talk to each other. You can consider them separately. Then, renormalized operators will, in general, be built by multiplying a vector of the 5 operators times a 5 by 5 matrix. And this is the structure this 5 by 5 matrix has. Okay? There is this piece here, which you see is block diagonal. Operator 1 is isolated, then operators 2 and 3, operators 4 and 5 talk to each other. And there is this piece here, which basically contains non-trivial elements whenever here there are zeros. Okay? Now, if chiral symmetry is preserved in their regularized theory, all these deltas are 0. Okay? So if you have chiral symmetry as a good symmetry, then you don't look at this. This is the identity. And this is the renormalization pattern. This is the way your operators here mix. And this is the only operator allowed in the standard model, operator 1, and you see it does not mix with anything else. When you break chiral symmetry, then these deltas are non-zero. So if you have a regularization that breaks chiral symmetry, like happens often lattice QCD that we will deal with later, then it is bad because you complicate the mixing structure considerably. These things, however, do not depend on the scale. All the scale dependence is hidden here. However, even if chiral symmetry is broken, in the parity odd sector, I told you can always split these things into parity even and parity odd halves. In the parity odd sector, the deltas are always 0. Now, if you only think about the anomalous dimension is the same for the parity odd and the parity even part of the operator. So then it is advantageous to use parity odd operators to work out anomalous dimensions, because then you don't have to deal with this extra mixing even if you break chiral symmetry. So that's what we'll do. What happens with adjoint fermions, however? With adjoint fermions, you have to work out again what these people did 15 years ago. And what happens is the following. Now I write explicitly the kind of operators you will have. You will have operators with no color structure, and you will have operators with color structure, where you have an insertion of some colored current here, whatever that color is. Okay? In QCD, these are fundamental generators. Now I have adjoint generators. And I will concentrate on the case of SU2, simply because the color identities are simple. So how does this work? In the case of adjoint fermions, here you are summing over color, otherwise this thing wouldn't be gauge invariant. And then you have this color identity here. You plug this in, you get some complicated linear combination of stuff, and then you can use spin fields identities to rewrite it in terms of linear combinations of operators which are contracted exactly in this way. In QCD, you have a different structure here, which holds for any group. And what you get out of these things is operators of this kind with flavors 4 and 2 exchanged and some other spin matrices. Here it is more complicated. Okay? Here what you get is operators where you have exchanged flavors. Here. No, here there is something wrong. Okay, you get two things out of this. You get operators where you have exchanged flavors 2 and 4, as before. And then you get this funny thing. You get operators where you have flavor all scrambled around, and you have charge conjugation matrices that allow you to build fermion fields from anti-fermion fields and vice versa. Okay, so you have a significantly different fields in structure with respect to QCD. And now you have a different basis, and you have to work out the mixing properties in terms of those. And this takes some work. It is actually much easier than it seems, because once you take all these operators and you put them into the kind of correlation functions I will consider later, you get exactly the same kind of contributions to the correlation functions as you do in QCD. So basically with what you have in QCD, okay, you compute the same kind of correlation functions, you combine them linearly in a different way, and you can work out the renormalization of operators with adjoint fields. So in practice, there is not much of a difference when it comes to, it is not that you have to compute new correlation functions. Everything is quite similar in the end from the technical point of view, but the basis looks quite different. And of course, this has to be worked out every time you change representation and group. If you now move to SU3 here, there will be extra contributions. This identity is a bit more complicated, and you have to work out the structure. Now, that was about renormalization. What happens with non-perturbative renormalization? I will be specifically interested in non-perturbative renormalization with running, and there are several experts in this here, so I will not dedicate a lot of time. What we are using is Schrödinger functional techniques, which have a long and noble story dating back more than 20 years. How does this work? What do you do to apply non-perturbative renormalization in this context? Okay, so you take your theory, say QCD. Let's think of QCD first, okay? You take your theory and you put it to live in a finite volume. A finite volume where you impose some particular boundary conditions such that it looks like a cylinder. You have Dirichlet boundary conditions in time, so fixed boundary conditions at time 0 and capital T, And then you have some periodic boundary conditions in space up to some global phase for fermion fields. And once you have the theory in this finite volume, you can define its free energy in terms of the partition function. And you can also introduce non-trivial Dirichlet boundary conditions by setting gauge fields on the caps of the cylinder to take some non-trivial values, which is equivalent to introducing some background chromoelectric field, fixed background chromoelectric field in this volume. And one very nice thing of this is that it is very easy to define a non-perturbative renormalized coupling in terms of the dependence of the free energy of the system on the background field. Okay, so when you change the background field, the response of the system, the response of the free energy of the system, allows you to define a non-perturbative renormalized coupling. And you fix the renormalization scale to the only physical scale that is available in the system, which is the finite size L of this box in space. It is fine to work in finite volume because you are working on renormalization. That's ultraviolet effects. That's something that knows about short distances, so it does not care whether the theory is in finite volume. So the advantages of this is that, first of all, it is a fully non-perturbative definition, for instance, of a renormalized coupling, and we'll come to composite operators. And this is something that can be computed easily in lattice QCD using numerical non-perturbative techniques. It allows to compute with massless fermions because the boundary conditions are such that exactly massless fermions can be used. This allows to work in mass-independent schemes very cleanly. And what is more important for me is that it allows to compute the renormalization group evolution non-perturbatively using some step scaling technique. So let me illustrate how that works for the renormalized coupling, for instance. What you do is you compute a fixed value of the coupling, which is fixed value of your box size, that is the inverse of the renormalization scale. And you do that at several lattice spacings, okay? What you do in practice is to take some lattice of some fixed length, you compute the coupling, then you take a lattice which is, say, double size of S times the size of the one before, you compute the coupling there, and this coupling in the bigger volume you call step scaling function, this sigma here. It is a function of the value of the coupling in this volume, and it is something which is related by this somewhat bizarre formula to the beta function. It is just a smart way of parameterizing the beta function. The nice thing is that you can compute both this thing and this thing in these lattices. Then you can go to some finer lattices, and to some finer lattices you repeat the game, and you can compute this at several values of the lattice spacing, take a continuum limit, and obtain this object, that is the beta function via this relation, in the continuum limit, no dependence on any cutoff, perfectly controlled non-perturbative stuff. So this is your way to trace the scale dependence of the coupling. And given this setup, you can do that across several orders of magnitude in the renormalization scale. So this is the kind of final result you get. This is the running coupling in Yang-Mills theory, QCD with 2 light flavors, QCD with 4 light flavors, computed by the alpha collaboration along the years. And I will show a few plots like this. In these plots, the points are the non-perturbative values of the running coupling, and the lines are perturbative computations of the running coupling. This is the UV. Here you have values of the renormalization scale, which are 10,000 times lambda QCD. This is the infrared regime. Here you have, this will be lambda QCD. This is a few times lambda QCD. So when you enter the hadronic regime, somewhere in here, is where you may expect to have sizable deviations from perturbative behavior due to the strong coupling nature of QCD. So whenever you see that the points deviate from the curves, that's non-perturbative effects appearing. Okay? And you see that they are not particularly large in the case of the running coupling, given the uncertainties of the computation. Now, what happens with composite operators? With composite operators, what you do is the following to trace the renormalization group running. This is again your Schrödinger functional. This is more schematically. This is time 0, this is time t, and time is running this way, and then space is wrapping around. Imagine that I want to renormalize a quark bilinear. Okay, that would be a need, for instance, to compute the running mass. So what I do is I take my bilinear here with some spin structure. This is living in the bulk of the Schrödinger functional. Here I have the boundary, which I call a 3-brane, just to be fancy. And on this 3-brane, I can construct some composite operator. I don't want to enter into the detailed structure, which acts as a source. It is some other kind of bilinear. And this is a 2-point function. Okay, so I compute this 2-point function. Then I compute another 2-point function, which is the 2-point function of whatever I put on the boundaries. This is there just to renormalize out whatever divergences you have in the boundaries. And you define renormalization conditions in this way. You take your 2-point function, you divide by this, and this is dividing out the divergences at the boundary. And what you impose is that this ratio of correlation functions in the regularized theory times the renormalization constant is equal to the ratio at tree level. And then you solve for this renormalization constant, which is then defined non-perturbatively. And then you can play again the step scaling game, exactly as I told you before. And then you construct step scaling function, which you construct with very good precision in the continuum limit, no cutoffs, no perturbatively, etc. It is this object here, and in this case, it is related to the operator anomalous dimension gamma by this formula. Sorry, I don't know what this G is. No, that's fine. So this is just a smart way of parameterizing the anomalous dimension of the operator in terms of something that you can compute with very good precision. And this you can apply, for instance, to the running mass, and this is a computation of the running mass in QCD with two-light flavor of quarks. That is Michele's work. And again, you see here non-perturbative points. So those are the blue dots. And you see perturbation theory. And this is a case where, amazingly, perturbation theory reproduces the running of the quark mass down to hadronic scales with remarkable precision. Okay, so this is a case where non-perturbative effects in the running mass are not really showing up down to significantly low energy scales in QCD. Finally, what do you do for the four-fermion operators I'm interested in? Okay, this is just a generalization of what you do for the mass. Here you have your four-fermion operator sitting in the bulk, and you have to construct a significantly more complicated correlation function. You have to contract this operator here with 3 different boundary sources, at least. This leads to a complicated 4-point function. On the other hand, by playing with choices for these sources and also with some free parameters in this setup, you have several choices of the renormalization scheme that will become important, for instance, in technicolor models. Okay? And then you impose a renormalization condition that is exactly as before. You take this correlation function, you divide out boundary divergences, and you impose this thing, solve for Z. And with that, you can construct a step scaling function that is related to the mass anomalous dimension of the operator. Now, this is it, however, for an operator that renormalizes multiplicatively. Okay, this is what happens for the contribution of the standard model. Then I have the operators that mix. You remember that I have pairs of operators that mix in beyond the standard model contributions. Then you have to generalize the condition, because then you have to determine a matrix of renormalization constants. What you do is to form a 2x2 matrix in the relevant sector. For instance, here I am looking at operators 2 and 3. You construct a 2x2 matrix of these ratios. Here you have to play with these choices of boundary sources and so on to get different numbers for the same operator insertion here, and then you impose a matrix renormalization condition of this kind. Then you get step scaling function, which is a matrix, and which is a t-ordered exponential of a matrix anomalous dimension. Okay? This is something that is algebraically complicated, but has no conceptual complications. Okay? So that's the setup. Let me now discuss some results. Let me first introduce very briefly some notation to understand the plots I will show. So these are again the renormalization group equations. This is the expansion of the beta function and any anomalous dimension in perturbation theory. And one thing that will appear in the plots is the so-called renormalization group invariant operator. The renormalization group invariant operator is obtained by taking a renormalized operator or set of operators, if you have things that mix, at scale nu, and multiplying it times this factor here. Okay? This factor here you can compute non-perturbatively, because you can compute non-perturbatively this evolution via the step scaling function. And this operator here happens to be something which is independent of the renormalization scheme. So it is a very convenient quantity to parameterize low energy effects. You want to give matrix elements of this operator instead of anything which is renormalized at some given scale, because then you will not have to specify what is your scheme and so on and so forth. So a very convenient quantity to look at is this running factor, this whole thing here, which connects the renormalized operator at some scale to the RGI operator, which you can think of as the operator run up to the ultraviolet, to the extreme ultraviolet, right? Okay, so these are results for the operator that contains the standard model contributions in Young-Mills and to flavour QCD. And here, just to complicate things, this is the running factor. This is n f equals 2. For Young-Mills, I have the inverse of the running factor because we change notation at some point. Okay, so let me concentrate here. n f equals 2. So this is more realistic QCD. So this is the operator that will control neutral meson mixing. This is this minus operator that appears. This, for instance, enters non-hadronic decays of kaons or Bs. This is the thing that will be below BK or BB, right? And here, with relatively large errors, in the Young-Mills case, the errors are smaller, you see that perturbation theory reproduces reasonably well the running down to scales of maybe 10 times lambda. Below, in the Young-Mills case at least, you see some non-perturbative behavior. For n f equals 2, errors are larger and you don't see it so neatly. But as a rule of thumb, non-perturbative effects are not huge for the standard model contribution when it comes to the running. Now, this is what happens, and these are new results which are yet to be published for operators that mix. These are operators 2 and 3, and I'm here focusing on corrections to BK or BB, say. So this would be the renormalization group running of beyond the standard model contributions to BK. And these are the 4 elements of the 2x2 matrix that embodies the running. Okay. So first of all, okay, notice the difference in scales. Okay, these are the diagonal elements. These are the left diagonal elements. This is quite small. There is not much mixing between 3 and 2, but there is a significant mixing between 2 and 3. First thing you see, and this is pretty generic of any renormalization scheme we find, it also happens in MS bar. It is not something that has to do with Schrödinger functional scheme. Perturbative truncation effects are huge. I mean, these are not things that are not converging well in perturbation theory. Here you are looking at scales which are almost 1,000 times lambda, and you see what kind of difference you have between leading order and next to leading order anomalous dimension. I mean, it is a large effect for at least these 2 matrix elements. It is not the case here. This is very small, but here you already see that perturbation theory is not converging well, even at high scales, for these operators. Okay. And also, you see, and it will be more spectacular for the other pair of operators, that in some cases, for some of these matrix elements, non-perturbative effects are quite sizable at low energies, even given the large errors we have on this computation, which has some numerical limitations. Okay? It is much more spectacular for the other operators. These are operators 4 and 5. These are the tensor and the scalar left operators, which means, again here, there is an element which is almost 0 in this mixing matrix in the running. But then 2 things happen. First of all, there are huge truncation effects in perturbation theory. Look at the difference between the leading order and next to leading order curves here. Look here where these things even cross at low energies. This looks a bit flabbergasting, but there is nothing mysterious. When you look at the renormalization group evolution equations, things are algebraically complicated, so this is bound to happen whenever there are large next to leading order corrections. And most importantly, you see that at low energies for some of these matrix elements, especially here, the non-perturbative corrections are quite large. I mean, they are things that are 15, 20%. Here, you don't even have anything like convergence of perturbation theory, even if this matrix element is small, etc. So, something that sort of surprised us is the fact that the running itself contains quite large non-perturbative effects and indications that perturbation theory is not working very well here. So, I mean, this is something we are finishing now, and we wonder whether this may explain some of the discrepancies that have been seen in the literature in the computation of beyond the standard model contributions to, say, PK, where different groups have obtained quite different results for some of the renormalized matrices.
So one anomalous dimension was change in sign.
Yeah. This is the step, sorry. No, right. This is the RG evolution operator, the matricial one.
What?
This is the matricial RG evolution operator.
So the
yeah,
one two was change of sign
it
from
changes
one
sign.
loop to two loop.
Yeah,
No, I mean the other one,
which one?
the upper. No, sorry. Yeah, the upper right.
Upper right.
Yeah.
You mean this thing here?
Yeah.
But this is simply that perturbation theory is converging so poorly that one shouldn't really look at this side of the plot. I mean, when you see these curvatures here, that is simply the breakdown of perturbation theory. It is the same here, actually. When you see these things cross, I mean, you look at the perturbative evolution equations, and you see that this will happen whenever the next to leading order correction is large. But one shouldn't look at it too much. It is simply a sign of the breakdown of perturbation theory. You start seeing weird things because you cannot trust.
Sign, principle.
Sorry?
You see it as a change of sign in the
Well, this is complicated because here you get a mixture of leading order next to leading order and mixed terms coming from matrix products. Okay, so the expressions are somewhat complicated. We can look at them later and you will understand better how the algebra comes about.
It's decreasing and then it's increasing.
Okay, so in the last 5 minutes, let me say something about fixed physics. Okay. So now I want to take all this technology that is well tested in QCD, and I want to bring it to the context of technicolor models. And this is your standard plot of the parameter space of candidate theories to display a conformal behavior. You have it there on posters in various versions. And what we will focus on, because it is something that is well studied and we control well, is minimally walking technicolor, which is 2 direct fermions in the adjoint of the gauge group sitting here in this plot. And there is quite some extensive evidence that it has conformal character. The mass anomalous dimension in this case is on the small side if it has to be a phenomenological impact. But as I said, it is something we control quite well. And this is work done by people here where the step scaling function of the coupling is sigma u, which is here divided by u, this is the renormalized coupling, and the step scaling function of the mass, again as a function of the square renormalized coupling, have been computed non-perturbatively. This thing here should bend down and cross 1 if there is an infrared conformal fixed point. It looks like it does here, although the systematic uncertainty is quite large. And then once you are convinced that there is an infrared fixed point here, you should come to this plot, look at the value of the coupling, and you would read off the mass anomalous dimension from this quantity here. Again, there are large systematic uncertainties here. Okay? This is what we knew of this theory. And as I said, what we wanted was determine anomalous dimensions of four-fermion operators in this model using all these QCD techniques I described. And one important thing here, I didn't stress this in the QCD case, but I will now. We have different several renormalization schemes. That is interesting here because if you find results that are quite independent of the renormalization scheme, that is very consistent with conformal dynamics. Okay, so we did lots of simulations. We proceeded in a way which is not what the alpha collaboration would do. For instance, here you compute fixed values of beta and nice ones and a few lattices, and then you use interpolation techniques to get the quantities instead of very carefully extrapolating at constant scale. So far we did just some preliminary rough analysis. So what we are computing, and I will show, is some approximant of the anomalous dimension that would become exact if the running is very flat, but it just gives you a glimpse of what is going on. So this is just to show the kind of results we get from our simulation. This is the anomalous dimension computed in the way I just flashed of the mass in this theory with the new simulations. And these are various steps with various colors coded here. No continuum limit so far, and probably there is no point in doing one, but this is just to show that we have relatively small cutoff effects and decent error bars if you just want to have a qualitative glimpse of what is going on here, and this you can compare with this kind of plot, which is quite different, but probably you can compare it with the black points here, although this is the step scaling function I was showing the anomalous dimension. Okay, so here are some results for fermion operators. We did first the multiplicatively renormalizable case, of course, which is the easiest one. Then we will take on matrices, and these are the two multiplicatively renormalizable operators. You remember there was a plus operator, which is in the standard model goes with BK. There is a minus operator, which in the standard model goes with some non-leptonic decays. Here, it's two operators you have in the game. And what I'm showing here is the crude estimate of the anomalous dimension obtained from one particular step scaling. And this here is what you get for the minus operator for 5 different renormalization schemes. And this is the plus operator for 5 different renormalization schemes. So there are two conclusions from this plot. One is that the anomalous dimensions are small, so nothing like these fancy things I was discussing before concerning Yukawa couplings are bound to happen here. The second thing is that different schemes give very similar results for the anomalous dimension. That is a very strong indication of being in the neighborhood of a fixed point. And if you want to compare that with QCD, this is, for instance, for this operator, this is Young-Mills, just to have good precision. This is the running I was showing before I was showing this plot. This is the running of BK. This is what happens now if you change scheme. Now you go to the infrared, and you see that between two schemes that are otherwise very well behaved, they are well behaved in perturbation theory, there is nothing fishy. Then in the infrared, you see a clean 10% dependence on the renormalization scheme in two schemes that we know are converging well. Okay. Here, the points are inside each other's error bars, so you don't see any kind of difference, like if I'm using. This is a check that when you change the step scaling, again, we are not taking continuum limits here, but we can at least compute the estimator of the anomalous dimension for various choices of the step scaling and compare the results, and basically we don't see differences. Certainly we don't see any differences between the error bars. So as far as continuum limits would be concerned, I don't think you can see this plot very well, but here you have error bars this size. Probably this is a safe or bit crude estimate of what the anomalous dimension is in the continuum limit, which is sort of enough to conclude that you are not getting large anomalous dimensions in this specific case. Okay? Well, that brings me to my conclusions. So the first goal I was aiming at here was to control the systematics of QCD renormalization for beyond the standard model operators that contribute to flavor physics. That is a precision game. I showed you what is the status of the unitary triangle right now. We have applied the alpha program successfully to four-quark operators that mix, and we have some intriguing hints that there are large non-perturbative renormalization or running effects which may or may not play a role in physics prediction. And then the second goal was to bring this technology to technicolor models, and we wanted in particular to explore what happens with infrared fixed points that may be there in minimal walking technicolor. We have shown basically that both the mass that we already knew, but also four-fermion anomalous dimensions are feasible. They look small, so you don't get fancy stuff in the infrared, and of course there is a lot of room, there should be a room, not goal, for improvement. I mean, you can use gradient flow, you can carefully rotate your Schrodinger functional to have further improvement. There are lots of technical stuff you could do. What I want to end up with is the remark that these mature precision tools we have in lattice QCD offer a very good deal of potential to treat this complicated physics, flavor or Higgs, quantitatively and successfully. And that's all. Thank you for your attention.